Thank you, Hagit. Thank you, Seth and Karen. And we are starting a blue session. This is a session mostly about coloring and node labeling and edge labeling, actually. And the first talk is given by Yannick Maus on a work titled Local Conflict Coloring Revisited, Lineal for Lists. So, Yannick, go ahead.
So, yes, this is a blue session, and this is joint work with Tigran Tonoyan, who's also at the Technion. And I think it's a very classic blue paper because it goes back to the first paper by Linial, which started this whole area. So we're in the local model, we have discrete synchronous rounds, and the complexity measure is the number of rounds. And what we want to compute here is vertex coloring, as you can see here in the bottom. And we are in the regime here where the complexity is mainly a function of delta, the maximum degree, except for this log star n term here. And this log star n term is because of Lineal's seminal lower bound. In the same paper, Linial also gave an algorithm, and it's a log star n round algorithm to color with delta squared colors, and it works for general graphs. But delta squared is a lot of colors, and usually what we want to have in the distributed setting is to color with delta plus 1 colors. Note any graph has such a coloring, and sequential greedy algorithm centralized can very easily compute such coloring. So Lineal's algorithm immediately gives an algorithm for delta plus 1 coloring, which has a runtime of order of delta squared, simply by just first executing his algorithm and then reducing 1 color per round. So then we've seen a bit of progress, reaching over algorithms which have a runtime of delta times log delta and then linear in delta. And now we also know sublinear in delta algorithms where the state of the art is roughly square root delta. So in this work, we also have an algorithm which has a runtime of roughly square root delta. So I think we didn't get approved for shaving off this log star delta. It didn't get accepted here for shaving off this log star delta here, but actually because our algorithm is, I think, is simpler, and more importantly, our main technical contribution, relates back the state-of-the-art algorithm here to Lineal's initial algorithm. So our main technical contribution is a list variant of Lineal's algorithm. So if you want to see how this main technical contribution implies the result below, you can watch the long talk. It's not too difficult, it's 2 slides, given the result above. So I will use the rest of this talk now to explain what do I mean by this, the list variant of Lineal's classic algorithm. So Lineal's classic algorithm is taught, I think, in any course, graduate course on this topic. And at the core, it has this 1 round color reduction procedure. So you're given an M coloring and you want to compute an K coloring. It just takes 1 round. This K is, think of it to be smaller, much smaller, but it's in the order of delta squared roughly. So roughly here, delta squared. And if you iterate this algorithm and take the IDs as the initial coloring and a few small tricks, additional tricks, you get Lineal's algorithm. So what we have is a list variant of this problem. So we take 2 rounds, but we solve list coloring. So in list coloring, each vertex has a list of available colors, and you need to output the color from this list. Then this number of colors here of Lineal's algorithm translates into a minimum list size requirement. So just ignore for this talk all these polylogs here. And let me instead now just say a bit about the proof. So Lineal's result is based on low intersecting set families. Our result is based on higher order low intersecting set families. So we need to talk about sets of sets. And because these algorithms just have 1 round and 2 rounds, I can also tell you what the algorithm is. So Lineal's algorithm is just each node selects a candidate color set. And how do you select it? Well, this low intersecting set family here helps in doing this. You do this without communication. Then you send these color sets to your neighbor, and then you pick a color which is not a candidate of any of your neighbors. And our algorithm has 2 rounds. And in the first round, or first without communication, you now pick many candidate sets of candidate sets. So it's a higher order version. So you pick many of these candidate sets here, and then you send the whole collection to your neighbors. Everyone compares, and then you pick one good candidate color set, and then you proceed just as Linial does. So if you want to know more about how this algorithm embeds into this general area of distributed symmetry breaking, you can also watch my ADCA talk, or you're invited to watch my ADCA talk on Friday, where I'll also talk more about this and related results. So I think, thanks. That's it. And now I'm open for questions.
Okay, thank you, Yannick. We have time for questions.
I can ask a question.
Yes.
So do you see a chance to get down to delta squared list coloring if you spend log star rounds? With a sufficiently small color space?
No, I don't know whether it's possible. We tried, of course, we tried hard, but even if we do the math super tightly, it immediately fails to get rid of this.
This would give a clean root delta plus.
Yes, yes, I would very much like this, but I don't know how to do it. But yes, it might be possible. So it's really not clear.
So I have a small question, Yannick.
Yes.
Can you just explain where does the log come from? The log C.
Wait, which one? The log?
Log C.
The log C. This comes because, well, we have this 0 round. We solved this in 0 rounds. We solved the problem of assigning each vertex a family of all these candidate sets. And this family has to depend on the color space in which the lists live in. So we need the list size to be large enough to actually make sure that for any possible list in this color space, we can assign a suitable family. So we need to, for every combination of a list and an input color, we need to assign one family. And the number of different families that we need here depends on the size of the color space. So
okay,
it's basically it's similar to Lineal's. In Lineal's result, you have this log n, because for every input color you need to have one set. And here, because we have 2 rounds, the log becomes a log. And yes, this is the main reason.
Okay, thank you, Yannick. If there are more questions, we will take them offline. We are moving now to the next talk. Okay, the next talk is titled "Coloring Fast Without Learning Your Neighbor's Colors," and the speaker is Alexander Nolin. So, Alexander, please go ahead.
So hi everyone, welcome to this talk. So I'm Alexander Nolin, as the boss was saying, and I would like to present this joint work between Magnus, Fabian, Yannick, and myself, and it's about the distance 2 coloring problem. So more precisely, what we studied here is the distance 2 coloring problem with delta squared plus 1 colors, where delta is the maximum degree of the graph, and in the convex model. So quick recap on the convex model, you have a graph. Nodes have unique identifiers on the graph. There are n nodes, and the nodes can only communicate along edges, and you have congestion. You cannot send more than log n bits in a given round on a given edge. So everyone is initially uncolored, and the goal is that at the end, every node has picked a color such that it has a different color than its distance to neighbors. So it would look something like this. Progressively, each node gets colored until at the end, you have no conflict. You have no 2 nodes at distance 2 from each other that have the same color. So as I said, delta is max degree of the graph. And we use delta squared plus 1 colors for the distance 2 setting. because of a very simple argument, it guarantees the existence of a coloring. So it's kind of easy to argue. If you are in the distance one setting, for example, imagine you have a partial coloring and you have delta plus one colors. Well, it's quite easy to see that any partial coloring can be greedily extended, right, to another coloring where you have less nodes uncolored. And so that shows you that every graph admits a delta plus one coloring. And with basically the same argument, you can show that a distance to any graph admits a delta squared plus one distance to coloring. So that's why we use this number of colors. And currently the best complexities are as follows for these two problems that I know of at least. So in the distance one setting, it's log delta plus poly log log n. And in the distance two setting, it's log delta times log n. And what we are doing in this work is improves its second complexity to log delta plus 2 to the square root log log n, which actually was the complexity of the distance one setting when we submitted the paper. So that's the question here of whether the two complexities match. But right now, they're not matching. So intuitively, what makes the distance two setting harder and higher distances harder is that there is no way you can learn your distance two neighborhood in less than delta rounds. There is just too much information to learn and not enough bandwidth. So the thing is, that means that since you don't know what your distance to neighbors have as color, you cannot just say, I'm going to try to pick some given color, knowing that none of your distance to neighbor are currently using it. So you have to gamble. You have to try things, not knowing whether your distance to neighbors are possibly using the color or not. You are trying things blind. So that's what makes the problem kind of harder in this setting. And a key part of our algorithm is a construction called almost click decomposition. So basically, it's a partitioning on the graph between sparse nodes that have many edges missing in their neighborhoods and almost cliques, which are small sets of nodes that look a lot like cliques. So on this graph, it would look like this. And along the way to our most efficient algorithm, we prove a log n algorithm that starts by computing an almost click decomposition. Then each color tries a random color, and you have this nice property that the sparse nodes have a lot of colors repeating in their neighborhood, and that helps color them later in the next step. So sparse nodes are dealt with quite easily. And then you have the dense nodes, the nodes that are in almost clicks. And for those nodes, what you do is you use advice from nodes that you are very well connected to, that are in the same almost click as you. And so that's where the main source of improvement. That's where we get the improvement over the last algorithm. The previous algorithm had to do something in phases, in log delta phases. It was running log delta phases of log n rounds, where you progressively reduced the degrees of nodes from delta over 2 to delta over 4, delta over 8, and so on. So, and we have managed to remove this thing. And then once you've done with that, you have so few nodes that you can do things like learning what colors you have available and so on. And that was already in the previous paper. But then you have so few nodes that it's easy to finish. The main procedure that gives the improvement looks something like this. Basically, when you have a node that is in a normal click, it can ask for help to its neighbors that makes suggestion of colors. Well, the issue is when you do that is although your neighborhoods are comparable, you can give bad advice because you're not exactly connected to the same nodes. And so we enrich this by doing another kind of help where you ask one of your neighbors to forward a help request where a node that is at a higher distance tests if it's connected to you, and then says, well, if I'm not connected to you, maybe you can use my color. And well, using these two kinds of helps, you can get that nodes get colored with constant probability when they alternate with those two helps randomly. And it's very sketchy, but that's the idea. And then if you want to go to sublogarithmic time, or the improvement comes from using the shattering framework. So reducing the problem to small instances of polylogarithmic size. And you have quite a few tricks like hashing and so on, and things specific to the distance to setting to get this thing. But the big part is making shattering work in this distance to setting, in this weird setting. And that's it. If you're interested in the paper, you can get it at this address. And yeah, and if you have questions, the floor is open.
Thank you, Alexandre. We have time for at least one question.
Sure. What happens with larger distance coloring?
Oh, so larger distance, I can already say something is that if you have a larger distance, even checking if the coloring is valid is hard. That's actually a paper I have with Magnus Alderson and Pierre Fregnaud. Like in the distance to setting, at least you can pick a random color, ask your direct neighbors if the color is not in conflict with anything, and if you hear positive feedback, you say, okay, I'm taking this color. With larger distances, you cannot even do that. So it really increases, it's hard. It's probably harder.
Is it clear that you need to be able to verify the coloring? I mean, I know that that's how most algorithms work, but.
Well, okay, so I don't have a formal proof that it's necessary, but I would say it's very likely that you're not going to get, I mean, you're going to have a much higher complexity with higher distances, unless you use so many colors that you have no conflict just by chance. I mean, if you have so many colors, you have no conflict, just because you're using exponential colors. Well, that also works, but with a low number of colors, probably harder.
Thanks.
Okay, thank you. I see that I skipped Seri. Seri, you want to ask your question?
Yes, thank you. The question is whether we can get anything better than delta squared plus 1 for distance 2 coloring. And the reason for the question is that we know that for distance 1 coloring, we can get something like O of alpha colors in polylogarithmic time, where alpha is the arboricity of the graph. So I'm wondering whether we can get something like O of alpha times delta for distance 2 coloring, or is there any combinatorial reason for which we can?
So I quick answer is I don't know, and I would say it's a good thing to study. One obvious research direction you also have is, in the distance 1 setting, you can also say that each color can only use degree plus 1 colors. You can kind of do the same thing in the distance 2 setting. So yeah, I mean, there are extensions there trying to do something like this. I mean, yeah, using less colors.
Thank you.
Okay. Thank you very much, Alexandre. Our time is out, and we move to the next. There are quite a few questions in the chat. You can answer them later. We're moving to the next talk, which is titled 22 New Approximate Proof Labeling Scheme, and Yuval Gil will give the talk. Yuval, go ahead.
So this is joint work with my advisor, Yuval Emek. And we start by talking about the model. So our work is in the field of distributed decision. So typically in a distributed decision system, we consider a configuration graph GS, which consists of a connected graph G, along with some bit string assignment S on the node. And our goal is to decide if GS satisfies a certain property. So formally, instances are configuration graphs that are taken from a universe U. And we want to distinguish between yes instances that come from a yes family and no instances that come from a no family, where the families are disjoint. So a typical example for a distributed decision mechanism is a proof labeling scheme. So proof labeling schemes were introduced by Coleman, Kuten, and Peleg. They involve a prover which is centralized and a verifier which is distributed. So given a yes instance, the prover generates its proof by means of a label assignment L that assigns to each node a label, which is a bit string. In response to that, the verifier at each node computes a Boolean value, and it does so locally, which means that the verifier at node V has only access to S of V to L of V and to the labels of all neighbors. So for proof labeling scheme to be correct, we have two requirements. First of all, if GS is a yes instance, then the prover generates a label assignment that makes all nodes return true. In this case, we say that the verifier accepts GS. If GS is a no instance, then for any label assignment, we ask that at least one node returns false, and we say in this case that the verifier rejects GS. A proof labeling scheme is measured by means of its proof size, which is defined to be the size of the largest label assigned by the honest prover. And basically, this is what we want to minimize. So since their introduction, there have been many studies into proof labeling schemes and some variants. One variant that we're interested in is that of approximate proof labeling schemes. So approximate proof labeling schemes were introduced by Censor, Hillel, Paz, and Perry. And they consider some distributed graph optimization problem and an approximation ratio. In these slides, we're going to consider minimization problems just for the sake of simplicity. The extension into maximization is very natural, and we address it in the paper. And we have two separate settings. So the first setting we call alpha approximate proof labeling scheme, or alpha APLS for short. In this setting, instances are what we call input-output graphs, which are configuration graphs where S encodes both an input assignment, which is assumed to be legal, and an output assignment that represents a proposed solution for psi. So what we want to evaluate is O's optimality. However, we may accept some instances that are suboptimal, but not too far from being optimal. So what does that mean? So we define yes instances to be IO graphs where O is a feasible optimal solution. And we define no instances to be IO graphs where O is either infeasible or not an alpha approximation. The second setting that we consider is that of alpha approximate decision proof labeling schemes, or alpha DPLS. And in this setting, we are given an underlying parameter K, and our instances are input graphs. So it means that the graphs are only given their input, and there's no output assignment. The input is assumed to be legal. And we want to decide if the optimal solution is bounded by K, or again, alpha far from it. So yes instances are input graphs where every feasible solution has objective value at least K, and no instances are input graphs where there exists a feasible solution with objective value less than K over alpha. So notice that in both settings, there are some instances which are neither yes instances nor no instances. And by definition, in these cases, the verifier may either accept or reject without affecting the correctness requirements. So in the previous work by Censor, Hillel, Paz, and Perry, they considered both settings. In the context of an APL, in the context of an APLS, they considered the problem of maximum weight matching, and in the context of an ADPLS, they considered the problem of diameter. Our goal was to extend the research into these settings, and this leads us to the results. So our results naturally divide into two. We have APLS results, and we look at some classical optimization problems. For instance, we look at minimum weight vertex cover, and we achieve an approximation ratio of 2, and a proof size of O of log n plus log W, where W is the largest node weight. We also look, for example, at the minimum edge cover on various graph families. And the second set of problems that we look at, and the second set of results are the corresponding ADPLS for the same problems. Something that I will mention briefly is that most of our results are due to two generic methods that we develop. We're not going to elaborate on them here due to lack of time, but they appear in the talk that appear in the YouTube channel. Also, we established some reductions that allow us to move from ADPLS to APLS, and these appear, and vice versa, and these appear in the paper. So thank you for listening, and you can ask questions.
Thank you, Yuval. We have a time for a question.
I have a question.
Go ahead.
Are these all deterministic? And if so, do you think there is any chance to have something randomized in this setting?
Yes, they are all deterministic. Basically, we follow the model that was introduced in the original paper. That's a good question about randomization. There is a setting for Merlin R2 protocols, for example, and from what I know, like some lower bounds in these settings apply also in the Merlin R2 setting, and these are lower bounds that use reduction from set disjointness or like two-party communication complexity. But for those problems, randomization might help. It's a good question.
Thanks.
Well, regarding Ami's question, we know that any deterministic PLS can be turned into a randomized PLS with an exponential reduction in communication complexity.
Yeah. So we can reduce the communication complexity by assigning larger labels, just the communication between the nodes. This is the randomized proof labeling scheme work. That's true.
Okay. Thank you very much, Yuval.
Thank you.
Do we have any more questions online? Well, in any case, we don't have the time. So we move on to the next talk, whose title is Classification of Distributed Binary Labeling Problems. It has a long list of authors, and Yuval Efron will present the paper. Go ahead.
Yes,
Yuval.
hi. I know the amount of Yuval's is confusing, but hopefully you can keep up. Well, in this talk, I'm going to talk about classification of distributed binary labeling problems. This is joint work with Alkida, Sebastian, Juho, Yannick, Dennis, and Yuka. My goal in this talk is to convince you of the following sentence, that the distributed complexity of homogeneous binary labeling problems on trees is decidable. We are going to break this sentence down into its components and understand them one by one, starting with distributed complexity. And by that, I am referring to the well-known local model of computation, in which we have a network of n nodes with unique IDs. Communication takes place in synchronous rounds. We have unbounded local computation inside each node. We have no bandwidth restrictions, and our complexity measure is the amount of rounds. Now for binary labeling problems, and due to lack of time, I will not define them for here, and I will refer you to the long version of this talk. But intuitively, in a binary labeling problem, we are tasked with labeling the edges of a given graph. In our case, it will be a tree, either red or blue, such that some radius 1 output neighborhood constraints are satisfied. For example, if we have this tree here, and the constraint is that each node needs to have at most one incident blue edge, then this labeling satisfies it. Examples for problems that can be described using this formalism include two coloring, perfect matching, and synkless orientation. Now, I will mention briefly what I mean by homogeneous, and by that I again intuitively mean that we're not going to care about leaves. And for leaves, every labeling of their incident edge is going to be a valid labeling. We only care intuitively about internal nodes. And now I can talk about the decidability and what do I mean by that. And that brings me to our main theorem, that the deterministic complexity in the local model of any homogeneous binary labeling problem is one of the following. Either it's O of 1, and not only that, we show that all problems solvable in O of 1 rounds can actually be solved in 0 rounds of communication. From there, we immediately jump to theta of log n with nothing in between. So in particular, theta of log star n disappears. And this is kind of cool because many well-known symmetry breaking problems such as maximal matching and maximal independent set are known to admit theta of log star n algorithms on bounded degree graphs. And so this means that these problems cannot be represented using only 2 labels. From theta of log n, we immediately jump to theta of n with, again, nothing in between. And we also have the unsolvable problems, which are basically the problems that have no feasible solution. Not only do we make this classification, but given the description of a binary labeling problem, we can very, very quickly find out its complexity and the optimal algorithm solving it. Although I did not define formally what a binary labeling problem is, I want to depict just how quickly we can find the complexity and the algorithm by the fact that it's just given by the following table. You see a binary labeling problem, and you simply check to which of these 7 types it matches. And by this, you can already know what is its complexity and what is the optimal algorithm solving it. To sum up, I will repeat our main result again, just to say it one more time, that the deterministic complexity in the local model of any homogeneous binary labeling problem is either O of 1, is either theta of log n, is either theta of n, or it is unsolvable. This is a good result because, well, this is the first step to the best of our knowledge towards automatizing algorithm design for distributed computing. You only get the description of the problem, and you can output the best algorithm that solves it. Regarding open problems, one can consider what about a classification of randomized complexity, or perhaps problems with more than 2 labels. For example, as I've mentioned, when one considers 3 labels already, more complexity classes appear, such as, for example, theta of log star n. Thank you.
Thank you, Yuval. We have time for questions.
Any questions about anything at all?
Okay, let me ask a stupid question. This is all about binary labels. Is there any hope for extending it for more than 1-bit label, like ternary labels, or maybe we need hyperedges for that?
Well, you mean if we have a trinary label, that would be like talking about 3 labels, which is what I've met here. And then already you would have like more complexity classes. For example, theta of log star n. And it seems that to classify exactly the full range of complexity classes that problems that can be described with 3 labels fall into is a much more challenging task, but it is a problem that people are working on to the best of my knowledge. I hope that somewhat answered your question.
You say possibly. Other questions?
Yes, I have one.
Yes.
Yeah, just a question. What do you mean by unsolvable? It means that there are no solution, or because
yes.
we can? Ah, okay. So the labeling is infeasible in this graph.
Yes.
Okay.
Yes.
Thank you. Thank you.
So the time complexity is 0 rounds.
Well, you can say that. You cannot solve the problem just by looking at the description of the problem. You can know that it cannot be solved.
You need to look at the graph also, maybe. So
well,
it may take more than 0 time to check, to decide if it's possible.
Well, if your constraint is, for example, that that we have some sort of partition of the graph into white nodes and black nodes, like, okay, this is getting a bit more convoluted and one needs to refer to the long version of the stock. But basically, for example, there is some, like, you can imagine a constraint where, like, on the one hand, you demand all vertices to output only red edges, but on the other hand, you demand all vertices to output only blue edges. Of course, such a constraint is not satisfiable.
So the order of quantifiers is that there exists some graph for which the constraints are not solvable.
Let me think about it for a second. But if I had to give a quick answer, I would say that no. Like, the actual description of the problem has a contradiction.
For any graph.
In it. Yeah, for any tree.
For any tree.
Not empty. Like, for any tree. Yes.
Yeah.
So,
okay.
For example, the requirement that there will be at least 1,000 white nodes. For this, you need, of course, to count that the size of the graph is at least 1,000.
It's a binary. It's edge labeling.
Yes. So like, all edges, at least 1,000. You could have a string of length 1,000, right? So
yes,
like
you could have a constrained string of length, say 1,000. Yes, but like our.
So you need to know how many, if you have a path of that length.
But
so you need to check the graph.
But like our decidability result is like outside of any particular graph. Like, you can think of this as like a Turing machine that simply gets the description of the problem without any particular input instance, and just outputs its complexity. There is no underlying input graph necessarily.
Okay, thank you. We're slightly over time, so thank you, Yuval. And we move to the next talk. The next talk is titled The Complexity Landscape of Distributed Locally Checkable Problems on Trees. And Yiran Chang will give the talk.
Okay, so I assume that everyone knows the local model. And so in the local model, there are a lot of distributed problems, but not all of them are interesting. And for example, for any reasonable round complexity function f, it is easy to construct artificial problems that realize this time complexity function, like gathering the IDs within distance f. And the point is that these problems are not interesting. And in order to get interesting results, it is important that we get rid of these artificial problems. And one popular way to do so is to restrict ourselves to locally checkable labelings. And so indeed, this class of problem excludes artificial problems that I mentioned in the previous slides. And it also includes most of the important problems that people are interested in the local model, like the maximal independent set and delta+1 vertex coloring. So this notion of locally checkable labeling was formalized by Nauer and Stockmeyer a very long time ago, but a systematic study of this subject began only a few years ago. And there are already a lot of interesting results, like what we have seen in the previous talk, and also what we will see in the next talk. And so in this talk, we will focus on one thing, that is, there exist several large gaps in the complexity landscape of LCL problems in the local model. For example, between log star n and log n, it is possible to show that there is no LCL problem whose deterministic complexity lies within this region. So in this sense, there is a gap between log star n and log n. And in this talk, we will focus on trees. And there are two prior works. So Chang and Petty show that there is a gap between log n and polynomial in n. And Liu et al. Show that there is a gap between square root of n and linear in n. And the main contribution of this work is to extend these two results to show the existence of the gaps for the remaining parts, like here and there. And in this talk, I will not be able to go through the proof. If you are interested in the details, please watch the YouTube video or read the paper. But at the high level, the way we prove this result is by unifying the approaches taken in these two prior works. And so in addition to proving the existence of the gap, we actually also obtain a decidability result, like in the sense of the previous talk. That is, we show that there exists a sequential algorithm that, given an LCL problem as an input, this sequential algorithm can decide which side of the gap this problem P belongs to. And now you might wonder, like, how efficient this sequential algorithm is. The answer is, unfortunately, this sequential algorithm cannot be efficient because this is a very hard problem. And it is possible to show that it is, in fact, exp time hard. So this rules out the possibility to have a polynomial time algorithm. And the way we prove that this is exp time hard is similar to a previous p-space hardness result. And so there are still a few interesting open questions for the complexity landscape of LCL problems. And it will be fantastic if you can solve any of them. So I think that's it for my talk. Thank you.
Thank you, Iran. Questions?
Yes. So what is the intuition behind all these gaps? Is it possible to give, why is it the case that in the local model there are these many gaps? Is there any intuition behind this, or at this time it's only different reasons here and there, and yeah, just intuitively, why these gaps exist?
So I think for different gaps, there are different reasons. For example, this log star n, the gap between log star n and log n, this is because that we can like create small fake IDs using lineal coloring. And in order to do this, you have to be given a sub-logarithmic round algorithm. And the reason that you can accelerate the algorithm to make it run in just log star n round is because Lineal's coloring algorithm takes log star n round. So this is the reason behind this gap. And I think for different gaps, there are different reasons behind them. So I think there is no unified reason. Yeah.
Thank you.
Okay. More questions?
So regarding the sequential runtime that you mentioned towards the end, the X time lower bound, you measure the time with respect to what is the size of the problem? This is just the description size of the LCL?
Yes.
Okay, so maybe we shouldn't be that concerned about, I don't know, exponential time or something like that, given that the description size is typically relatively small.
Well, I think the description size is large because we have to like enumerate like what is an acceptable configuration and what is not. I don't know. I mean, if the
let's put it this way, for the problems we are usually interested in, we can describe them fairly easily, right? I don't know, maximal matching or whatever. But sure, I mean, it's still, that's of course a valid result.
I guess so, but I still do not think that the algorithm that I have in mind is going to be efficient because I mean it's a exponential of exponential of, I don't know. There are, and the constant seems to be large.
Okay,
so,
sure.
Okay, we're slightly over time, so thank you again, Iran. And and we move on to the next talk, which is actually a brief announcement titled Distributed Graph Problems Through an Automata-theoretic Lens. And Jan Studeni will give a talk. So Jan, please go ahead.
Okay, hi, I'm Jan, and I'll describe to you our paper named Distributed Graph Problems Through an Automata-theoretic Lens. This is a joint work with Iram Chang and Turka Somela. Let me start by giving you a high-level picture of what we are trying to solve. We are given a graph problem pi, and we want to efficiently answer the following three questions. Is pi solvable for any graph? Can pi be solved efficiently? And what is an optimal algorithm for solving pi? Of course, this is a very broadly posed question, so we study the following special case. The graph problems that we focus on are locally checkable labeling problems. So, for example, computing vertex coloring or edge coloring is a locally checkable labeling problem, consistent orientation, maximum matching. And moreover, we restrict our attention to unlabeled paths and cycles. These graphs can be directed or undirected. And for the model of computing, we give the answers in the classical model of local model of distributed computing. In this model, we know that LCLs on cycles and paths in the local model can be either constant round solvable, log star solvable, or global. But the proofs give only the separation between the classes. They do not tell anything about whether a given problem falls into constant round solvable, log star solvable, or global. And as a first step, Brent et al. Showed that there exists a simple and efficient characterization for unlabeled directed cycles. So the question is whether it can be extended. And we show that indeed there exists a polynomial time algorithm characterizing LCLs on cycles and paths in all except one special case for which we prove an NP-hardness result. How do we achieve it? We view the LCL problems as automata. And now I'll quickly show you how. So when we are given an LCL problem, or rather is a description on the left, we describe it or we convert it to a non-deterministic finite automata over a unary alphabet. This automaton fully describes the LCL problem, and for the edge-free coloring, it is shown here. And once we have the automaton, we classify each state into one of the 6 types. These types on the high level represent how easily can we return to a given state. All of these types are polynomial time computable, and there is a direct correspondence between the types and the round complexity of a given problem. So for example, in the edge-free coloring, it has a flexible state, so it will be a log star solvable. To summarize, we give an efficient characterization of LCL problems, and the key technique was to use automata to view them. Thank you, and I'll answer any question you might have.
Thank you, Jan. I'm afraid we're out of time, so questions will be taken later or in the chat. And we move on to the last talk of this session, which is a brief announcement titled Efficient Load Balancing Through Distributed Token Dropping. And the talk will be delivered by Barbara Keller. Hello, Barbara.
Hello. Yes, I'm here. Okay, let me share the screen. My PowerPoint just died. I guess I have to restart it.
Maybe we have time to take some questions for Jan. I have a question for Jan, actually. Is there any relation between your automata approach to cellular automata?
Sorry?
I'm asking, is there any similarity between your approach, your automata-based approach to the theory of cellular automata?
I don't think so. I would probably guess not, as we use it for the proofs and we give the connections with the automata, with the non-deterministic finite automata.
Okay. Other questions, comments? Barbara, are you ready?
I think it should go now.
Okay, so let's...
let me try again.
So thanks, Jan, again, and we switch to Barbara's talk.
Okay, so sorry about that, and welcome to my brief announcement about efficient load balancing through distributed token dropping. This was joint work with Sebastian, Joel, Jukka, and Yara, and myself, of course, Barbara. So what do we talk about in this load balancing? So we also talk about the local model, and I now skip the description. So n is the number of nodes, delta is the highest degree in the graph. And what we want to do is to assign clients to servers. So we have 2 kinds of nodes. And if this setup sounds familiar to you, it's maybe because you already heard about it in the best paper presentation. So we look at the same problem. So we have clients and we have servers. And if we assign the clients to the servers, they get a load. And the goal in the semi-matching is to minimize the sum of the loads. In this work, we looked especially at this stable assignment. This is a locally optimal semi-matching and not a sub-optimal semi-matching. And what do we mean by locally optimal? We mean that no client has an incentive to unilaterally switch servers. So if a client switches the server, it will not get a lower load on the server. Then we have a stable assignment. It was also proven that a stable assignment is a true approximation to an optimal semi-matching. So that's a good thing. Then the general idea is that we start with an empty assignment. We temporarily assign at most 1 more client per server. And then we introduce a new technique, which we call token dropping, to balance this load. And then once we did that, we keep on repeating these steps until every client is assigned to a server. So how we do this instance from the original graph to the token dropping graph instance, if you're interested in that, you have to watch the longer video or read our paper because I don't have time here. But let's take a look at how this token dropping actually works. So we have nodes on different levels from 0 to L. And then there are nodes and edges and tokens. These are these blue items. And the rules are pretty simple. Tokens want to go down the graph, and any edge that's traversed can only be traversed once. And how we do it in praxis is every unoccupied node, which has at least 1 parent with a token, proposes to the parent. Then any parent who gets a proposal will accept one of them, if there are several ties are broken arbitrarily. And then these tokens are sent down. And this thing is just kept repeating, like the children propose, the parents accept, and the tokens are sent down and the edges are removed after that. And we do that until all of the tokens have reached the minimum level they can reach. And you can see it's very straightforward. The analysis was a bit more complicated than the algorithm by itself. And that's already what I wanted to tell you about it today. So what is the state of the art and what are our contributions? So Chikrinov et al. Proved in 2012 that this is a 2 approximation and their running time is O of delta to the power of 5. We could reduce this running time with this algorithm by delta to the power of 4. And you can see there is a C in our running time. This is the degree of the clients. We also have shown a lower bound of delta. And yeah, we have the same approximation as Chikrinov because we just use the same stable local assignment. Yeah, I don't think I have time for this. So that's it.
Okay. Thank you, Barbara. I guess if someone has a short question, we can accommodate that. Otherwise, anyone with a short question?
Yeah, please. Would that work for weighted case? Can you have a weighted semi-matching?
Oh, actually, I didn't think about that. I mean, you can, of course, think about the weighted semi-matching. You can define that, but I'm not sure how our token dropping would work because what we do is like these tokens is this excess load. And I'm not sure if we then would want to somehow get this token down differently because there is different loads. But
maybe the tokens should have weights.
Yes, one could think of that, but then I wonder if one should prioritize the heavy tokens because they should fall down faster than the others, something like that.
Okay, so thank you, Barbara. This concludes the 6th session.